Markov Chain Monte Carlo is a framework for generating samples from probability distributions. But why is it so popular? Let's assume we have a probability distribution describing the efficacy of a new treatment in a group of patients. How do we use it to answer questions like, how effective is the new treatment on average? Or how similarly did participants respond to the treatment? These questions can be formulated as expectations of functions with respect to our probability distribution. However, in most real-world situations, these expectations cannot be computed by hand. This is commonplace in Bayesian statistics, where the distribution we want to make inferences from is the posterior distribution. The posterior is computed using Bayes' rule, by multiplying the likelihood by the prior and dividing by the evidence. Unfortunately, computing the evidence is difficult. So how are we supposed to make inferences? We are stuck with a ratio of difficult integrals. This difficulty arises in two ways. Either the evidence contains too many terms to compute in a reasonable time, or it has no closed-form solution. One example of computational difficulty is computing the evidence of a finite mixture model, which requires summing over k to the power n terms, where k is the number of mixture components and n is the number of data points. Even a tiny two-component mixture model with 30 data points requires summing over 1 billion terms. An example of an analytical difficulty is logistic regression, with a normal prior for the model coefficients. This lacks a closed-form solution due to a difficult product of exponentials. One approach to solving this problem is to use a grid approximation. Let's say we compute the proportional posterior distribution of a logistic regression model. We cannot access the actual posterior distribution because we cannot compute the evidence to ensure it integrates to 1. Instead, we can define a grid, evaluate the proportional posterior at equally spaced points, and then divide each value by the sum over all evaluations. This produces a discrete approximation to the distribution we want. In this example, I've simulated 25 data points from a logistic regression model with intercept and slope values of 2 and 1.5. Calculating expectations of discrete distributions defined over small grids like this is easy. It is equal to the sum over each value multiplied by its probability. We can improve the approximation by increasing the grid's granularity. The main issue is its scaling to high dimensions. Let's say we have a 100-dimensional distribution, and for each dimension we split the range into 1,000 evaluations. This means a huge number of function evaluations, about 10 billion multiplied by itself 30 times. Most of the evaluations in this grid will make little or no contribution to our expected value estimates. This is a result of the geometry of high-dimensional probability distributions. The most probable parameter values are found in the typical set. We'll get more into this in a later video, but for now, imagine this as a thin surface of a bubble where almost all the probability mass lies due to the interaction between volume and probability density. Instead of approximating the distribution exhaustively, we are better served by drawing independent samples from it and using the samples to estimate expected values. Samples from high probability areas will be drawn more frequently, so this is a natural way to capture the important typical set without having to look for it. Forming numerical estimations from random samples is called Monte Carlo estimation, named after the Monte Carlo casino in Monaco. The Monte Carlo estimate of the expectation of a function with respect to a probability distribution is the sample mean of the function evaluated on random samples from that distribution. An important theoretical guarantee of Monte Carlo methods comes from the central limit theorem. As more samples are gathered, the distribution of the estimate approaches a normal distribution, centered on the expectation with a standard error equal to the distribution's standard deviation divided by the square root of the sample size. This has a nice implication. Quadrupling the sample size reduces the error by a factor of 2, allowing us to target a desired error in a principled way. This is a significant increase in efficiency over grid approximation, as we only need a handful of samples to start making accurate estimates. But to use this guarantee, we still need a scalable algorithm to generate samples. Otherwise, we have simply moved the problem somewhere else. Rejection sampling is a straightforward algorithm for generating samples from a probability distribution. It requires two things: a proposal distribution G that is easy to sample from and captures the shape of the target distribution, a constant C to multiply the proposal density by, so that for the entire support, C times G is greater than or equal to P of X. To generate samples, first propose a value by sampling from G, then sample a uniform random variable between 0 and the value of the scaled proposal at this point. If the value of this uniform sample is less than or equal to P of X, keep the sample, otherwise reject it. We can repeat this process until the Monte Carlo standard error of our estimate is small enough for our needs. The number of rejected to accepted samples in the plot gives us an intuitive sense of rejection sampling's efficiency. The acceptance rate is the ratio of the area under the target distribution to the area under the scaled proposal, because the algorithm is designed so that proposed points are uniformly distributed under the scaled proposal. The higher this value, the more efficiently we can generate samples, since a larger proportion of compute time is spent generating accepted samples rather than rejected ones. The acceptance rate for this example is 46%. Rejection sampling also struggles as the dimension of the parameter space increases. Let's look at how the acceptance rate changes with dimension for a simple scenario with Gaussian target and proposal distributions. Set the target distribution to have a mean of 0 and a standard deviation of 1. Set the mean of the proposal distribution to 0, but give it a standard deviation slightly larger than 1. This creates a flatter distribution, but allows us to find a constant to multiply it by so that it bounds the target distribution. Now, consider three scenarios for the proposal distribution: a standard deviation of 0.01%, 1%, and 5% larger than the target. If we plot the acceptance rate as a function of dimension, it is close to 1 for low-dimensional problems, but drops off quickly as the dimension increases. Once a certain point is reached, the volume difference becomes huge, so almost every proposal is rejected. Another sampling algorithm is importance sampling. This approach also uses a proposal distribution, but unlike the rejection approach, all samples are kept. Each sample's contribution to an expectation depends on the relative likelihood of the sample under the target density compared to the proposal density. If we assume the common scenario of an easy-to-evaluate probability density known up to a constant, we can write the expectation as follows, introducing the proposal density g of theta. Note that the expectation has not changed because g cancels out. With a little algebra, we can show this is the ratio of two expectations with respect to the proposal distribution. These can be estimated using the Monte Carlo procedure introduced earlier. Importance sampling is a weighted mean of samples from the proposal distribution, where the weights compensate for over or underrepresented values. These are called importance weights. Let's use the same proposal and target distributions as before. First, I draw 250 samples from the normal proposal distribution and give each a weight of 1 on the graph. This matches their weight in a standard Monte Carlo estimate using independent samples from the target. Next, I calculate the importance weight for each sample and add its contribution to the estimates. Notice that the importance weights now reflect the peaks and valleys of the target, where the proposal density was mismatched. Checking the distribution of importance weights is an important diagnostic step. Ideally, we would choose a proposal that produces a distribution of weights with a low variance. Unlike rejection sampling, we can't treat each draw as an independent sample from the target. That's where effective sample size comes in. It tells us how many independent samples from the target would give the same estimator precision as the 250 weighted proposal samples. Unless the proposal is good, the effective sample size will be less than the total number of samples drawn. Importance sampling can fail badly if the proposal distribution has much thinner tails than the target. Suppose we run the importance sampling algorithm again, but halve the variance of the proposal distribution. Checking diagnostics as we go, things seem reasonably well behaved. But the longer we run it, the clearer it is that the estimate is choppy and erratic. This is most obvious when the 250th sample is drawn, because it is a very rare sample from the proposal in a region where the target has much thicker tails. This causes a big shift in the Monte Carlo estimate and a sharp drop in effective sample size. If we didn't know the true value of our estimate, as would be the case in practice, we may have been tricked into stopping the algorithm due to perceived convergence before ever seeing this sample. Things get even worse as the number of dimensions increases because the multiplicative difference between typical and large weights grows exponentially with dimension. This means that eventually, even very good proposal distributions will fail. Markov Chain Monte Carlo brings together two ideas. Think of Markov chains as a way to generate samples, and Monte Carlo as a way to estimate expectations with them. A Markov chain is a sequence of random variables with a special property. Given the current value in the chain, the next value is independent of the chain's entire history. This is a conditional independence relationship. You can picture this like a bicycle chain, where each link connects to the one immediately before and immediately after. These connections reflect how each random variable in the chain participates in the dependence structure, as an outcome of the previous step, and as a condition for the next. So how do we use a Markov chain to generate samples from our target distribution? The key lies in the design of the transition probabilities. Let's look at an example. Suppose our target distribution is a categorical distribution over three outcomes, A, B, and C, with probabilities 0.1, 0.4, and 0.5. We can construct a transition matrix according to the simple Metropolis algorithm. We can draw this as a state diagram. Each node is a state. These are the values the random variable can take, and the edges show the probabilities of moving between them. Let's begin in state A with probability 1. At each iteration, the sampler moves from state to state according to the transition probabilities, recording its history as it goes. At the same time, we can calculate the new distribution over states by multiplying the current state distribution by the transition matrix. If we were simulating a large number of chains, say 1000, simultaneously from the same starting distribution, then the number of occupants of each state would be split according to the current state distribution. After 10 steps, the state distribution converges to the target. This is because the Metropolis algorithm designs transitions so that the chain's stationary distribution matches the target distribution. The stationary distribution has the nice property that it is invariant to further evolution. So, if we run a long simulation from this point, the chain's history can be treated as if we had drawn samples from the target distribution, since the frequency with which states are visited matches the target probabilities. So why is MCMC usually a better choice for high-dimensional problems? Here are some rule of thumb scaling guidelines based on the number of iterations required for an independent sample. Rejection sampling struggles because the acceptance rate shrinks exponentially in dimension due to the volume difference between the target and scaled proposal distributions. Importance sampling fails in any dimension if the distribution of importance weights has a long right tail. In high dimensions, this gets worse because the multiplicative difference between typical and large weights grows exponentially. Both methods require a proposal distribution that is a very good approximation to the target distribution. Otherwise, errors are amplified exponentially, making independent samples extremely expensive to compute. MCMC avoids this issue. It uses a local proposal distribution to move through the support, improving step by step. The efficiency of MCMC depends on how quickly the sampler moves through the distribution. In the worst case, where the target distribution is explored using a random walk, the number of iterations between independent samples grows linearly with the dimension size. This is great news because the exponential scaling is avoided. But bear in mind that MCMC is far from perfect and still requires careful tuning to work well. I originally planned to make a video on Hamiltonian Monte Carlo, but as the list of prerequisites grew, it became too much for one video. So I'm making this the first in a series that will cover the background needed for HMC, leading up to a final video on the topic. In the next video, we'll look at what makes high-dimensional distributions so difficult to sample from, which will motivate the need for powerful MCMC samplers.